And this is about localization. Okay, so there's kind of two versions. For rings. And for modules. And the rings one is really kind of a subset of the modules one, but let me give the ring setup. Okay, so let's do the ring version. Okay, so the setup is that so we have R as a ring, and S here, a subset of R, is a multiplicatively closed set. Closed set. And 0 is not in this multiplicative set. Okay. In particular, since it's multiplicatively closed, it has no zero divisors. Or sorry, it has no nilpotents. It can have zero divisors. Okay. And so we define, so the localization, so that's no nilpotents. So the localization of R at S is the ring RS. Okay, so there's a couple notations, right? So one is S inverse of R. Another one is RS. So this is the set of R over S, where R is in R and S is in S. Okay, so this is two notations for the same thing. The same thing. Okay, and we have that R1 over S1 is equal to R2 over S2 if and only if there exists some S3 such that an S such that so S3 S2 R1 minus S1 R2 is equal to 0. Okay, and then addition and multiplication work the same way. So R1 over S1 plus R2 over S2. So this is S2 R1 plus S1 R2 over S1 S2, right? And R1 over S1 times R2 over S2 is R1 R2 over S1 S2. Okay, so this is the addition multiplication rules. And so the key point here is that now we've added this thing here, so that anything that is killed, right, by an element of S3 is now 0. Okay, this is a very important distinction. Okay, so so the official definition, right, is, so I'm doing it as pairs here, but really we have kind of equivalence classes of pairs of elements, R and S, right? That's how this is officially defined, but it's these rules here. And this thing here tells you the equivalence class, this equivalence relation, this thing that's by the red over here. Okay, so the module version is rather similar. So the module version okay, so now you take M in R module, and you take S as subset of R, a multiplicatively closed set. Not containing 0, not containing 0. And then you define the same thing. You define S inverse of M. This is M of S. This is notation for the same thing for the localization of M at S. So this is the set of M over S, where M is in M and S is in S. And so then you have the same exact rules. So you just don't have a multiplication rule. So same rules, right? M1 over S1 is equal to M2 over S2 if and only if there exists some S3 in S such that S2 M2, or sorry, S2 M1 minus S1 M2 is equal to 0. Okay? And then M1 S1 plus M2
Where's the
S2.
S3 in that?
S3. There you go. Sorry. Let me fix this. Yeah. This S3 is super, 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 super important. Okay? The thing, this is where everyone messes up their time learning this, right? Is this S3, right? Because in the normal fraction field, we don't have this S3 condition. In this S3, the localization maps are no longer injective, right? So this is if and only. So this is, sorry, yeah, the S3 is super important. So this is S2M1 plus S1 M2 over S1 M2, S1 S2. Okay, and so now both of these come with a localization map. Okay, this thing comes with a localization map from M.
S1 plus S2?
Uh,
On the bottom?
nope, S1 times S2. Because you have to have a common denominator. Did I put right plus before? No. Okay, this is the localization map here.
Can you talk a little bit more about, you were mentioning that the map is not injective and the difference?
Yeah, I'm going to give you an example. Yeah. Maybe we should do, yeah, we'll do an example. M is M over 1. And we'll do this LS R to S inverse R. And so this thing sends R to R over 1. Yeah, this map is in general not injective, right? So the big warning is not injective in general. Okay, so all right, so let's do a good example. So obviously, the obvious example, right? Let me just get this out of the way. If R is a domain, and S is R with 0 removed, then S inverse of R. So the localization at this set is the fraction field of R. This is the fraction field. Okay, and the localization of any domain is a domain. Okay, so there's kind of two, the two most important types of localizations are the following. So there's two important types. Okay, so one is if if F in R is not nilpotent, then we can consider the set S, which is 1F, F squared, F cubed, so on. And then you get RF, which is R S of F, which is S of F inverse of R, which is R1. So this is just like all these notations for the same thing. Okay, it's like some like Lord of the Rings introduction. Goes by many names. This is okay. These are all the same ring. Okay, essentially what you're doing is you're removing, you're allowing F in the denominator. Okay, that's the way you should think about it. The other important case is, so this is localization at an element, is that if P is a prime, it's a prime ideal, then S looks like R set minus P is a multiplicatively closed set. And then this gives us, okay, so this is a terrible notation. So there's, so R, let's do this, R minus P inverse, right? And then this is R, sorry, R minus P inverse of R. And then we do something terrible, okay, which is we write this as R sub P. Okay, so this is not an element P, but this is an ideal, a prime ideal. Okay, so this is the localization at a prime ideal. Okay, so there's two important things here, is that in this example here, this one says, so this one allows F in the denominator, right? So this thing here does not allow P in the denominator. Of P in the denominator.
Wait, but the notation is the same?
Yeah, that's the crappy part, right? Is that this R sub P says that you're removing P when it's a prime ideal. That's why this is a bad notation. This is kind of a crappy notation. But I didn't make it, you know, but this, it's a little bit bad. I mean, it is convenient at times, right? Because you don't want to write R set minus P every time. And this is so common, right? Okay. So let me do a quick example. And then I guess I'll draw these pictures. I'll draw the picture once right now. Okay, let me draw the picture once right now. So spec of RF. So this looks like, all right, so this is spec of R set minus V of F. So you've kind of like removed everything here, right? So I'm allowing denominators that vanish along this. So as long as I remove that from the space, then I'm okay. And so this one here is that if you have a prime ideal, so here's spec R, and here's P. So if here's P, then spec of R of P is like a neighborhood. This is like a neighborhood around P. So like if P is, so one way to think about it is like, so here in C2, in A2, right? So here at the origin, if P is equal to XY, so this is spec C of XY, right? So you're really allowing everything but things that vanish at XY in the denominator, right? So this is really everything but things that vanish at xy. So so this thing. Okay. That vanish at 0, 0 allowed in the denominator. Okay, that's why it's kind of like localizing. This is why it's called localization, right? Is because we're kind of going to a point and then we're taking the functions that are okay at when you evaluate at that point, right? So these are the functions that make sense at 0, 0. I'm allowed to plug in 0, 0 into those things. Right? And so here you've kind of localized away from this closed set. So this is the bad set. So in this set here, R of f, this is where the denominator goes to infinity. That thing that I've removed there. That's supposed to be the vanishing set of f. So like this could be like the x-axis or something. Okay. So let's do an example of this first type here. Okay, so maybe I'll just start this example, then I'll do it again next time. Okay, so kind of the sub-example. Maybe I'll draw the picture. Okay, so this is of the first type. So if we take R to be C of xy, mod xy. Okay, so geometrically, right, this thing is, so these are two axes. This is the y is equal to 0 axis. The x is equal to 0 axis. Okay, and now I'm going to take f as above to be x bar. Okay, so we're looking at the set S of f, which is 1 x bar squared, x bar cubed, dot, dot, dot. So this thing is killed by y bar. Okay, so like I said before, we're removing the set where this is 0, right? So we're going to remove, this is v of x bar. So this is what we're going to remove. And so we expect this thing to be like the line. So, okay, so let's do this. So we expect the thing to be a line with a point removed. Okay, so let's do this. L of x bar. Okay, so there's this is a notation for localization at a single element. I should have said that. I'll do this again next time. But you have R goes to R of x bar. Okay, and so this looks like C of xy, xy 1 over x bar. Okay, now what I wanted to show you is that y bar over 1 minus 0 over 1 is equivalent to 0, right? So is this true? Well, this is true if and only if. So there exists some S3 in S such that, well, S3 times y times 1 minus 0 is equal to 0, right? And so this is true, right? S3 is equal to x bar, so I should put bars everywhere. S3 is equal to x bar works. So this is in the kernel. Okay, so now okay, and so what you get is you get something like so now what happens is that this gets killed and this gets killed, right? And so this thing is isomorphic to C of x 1 over x. And this thing here Well, this is just like what I said. This is this line with, sorry, it's the other line. Let's see, the x coordinate, let's see, we removed, it's only the x-axis, I guess. So we have this line, and then we've removed the origin. So this is the drawing of spec of c of x, 1 over x. So we removed the denominator there. So yeah, so localizing, so yeah, so this gives an example. And I'll repeat this again in the next class. Yeah, so if you guys have any questions, I will be hanging out for a little bit. Yeah.
Thanks, Taylor.